All right, so new topic today. So we're going to talk about hashes. And a hash is a data structure that's used for storing and retrieving information, okay, which is what most of our data structures are used for. And they're closely associated with associative memory. So what's the basic concept of an associative memory? We have entries in our memory that are somehow linked to one another. So you can get from one entry to another somehow. An array is not a very associative memory. The way we access elements in an array is we use an index to go into the array, and out comes the element stored at that index. And if we want to know, say we want to store a set of information like name and what your job is. And we want to store this information inside a computer. So we could make an array with two columns in it, right? So an n by 2 array. And the first column represents a bunch of names, and the second column represents a bunch of job descriptions. And if you want to know what Izad's job is, you go through that array looking for the name that matches Izad. And if that's entry 13, then entry 13's job description is Izad's job description. And if we don't like two-dimensional arrays, we might do this with two arrays, a job array and a name array and a job array. And the first entry in the name corresponds to the first entry in the jobs, and so on and so forth. And we can search through the names, find a particular name, and that index gives us the job description that goes with that. And so we might have, entries like Izad and Nick and Scott and Tina. And Izad teaches electrical engineering, and I teach CS, and Scott teaches CS, and Tina teaches mechanical engineering. And so these would be two arrays, and we'd need to somehow keep track of the fact that there's 4 entries in these arrays. And now if you want to know what does Scott do, you run a for loop from 0 to 3, you check name bracket I to see if it equals Scott, and if it does, then you just print out jobs bracket I, and it shows you CS. So that's how we would solve this problem of storing pairs of data just using an array. And we can do this with lists, right? We could have a list where each node contained a name and a job, and we could move through that list until we found the appropriate name. And we could do this with a binary tree. We could have each node store a pair of pieces of information, a name and a job. We could make it a search tree based on name. And now you can take anybody's name, and in log n operations, you can move through your tree, find a node that contains that name, and then the job piece of that node tells you what the job is. So we can do this with other data structures, but with a hash, we're going to be able to do this in general in an order one way. So we can pull information out of a hash in a fixed amount of time, regardless of how much information is in the hash. That's the ideal. That's a theoretical hash. Okay, it's the most efficient order of complexity that you could hope for. You can have 1 billion things in your hash, and when you want to find out the job associated with a name, it takes you this fixed amount of time. Now, it obviously doesn't work like this in all cases, because that would just be nirvana. But in a lot of cases, if you set this up right, it's order 1, independent of the size of the hash. And a hash works as an associative memory. So we talked about this a little with respect to bash. We talked about it with respect to awk. The idea is we could have an array. So I don't know, I'll just call it data, because I can't think of anything better. And instead of being indexed by integers, we can index this array by strings. And so data bracket quote Izad contains the element EE. Data bracket quote Nick contains the string CS. and so on. And so this is an array we can index with these strings instead of just with integers. And if we ask for data bracket Barney the dinosaur, it'll come back somehow and say there's no entry in that array with that index. But if we ask for data bracket Carol, it'll come back and say, mechanical engineering or something. So this is the setup for an associative array. Okay, it's indexable by something other than integers. And the associative part is that, this field over here is associated with these keys, basically. And so we'd sometimes think of these as keys and data. And so the hash, or the associative array, is a collection of key data pairs. And this is a really powerful way to organize information. It lets you do all kinds of things more efficiently. And we've seen it in Bash, we've seen it in awk. It's also available in C. There's a collection of libraries, actually, that will let you work with things in this way. So the original name was Dbm Database Manager. And on newer versions of Linux, this got replaced by GNU Dbm, which was the open source version. And when I went to look for it last night, I couldn't find it, so I think it's been replaced by NDBM or something else. But I put it back on our server at least. So let me show you what some code looks like. Let me get my big window up, though. So here's some code. So usual include files, but I also include gdbm.h. That sets up some symbols for us. And we can do the following operations. We can say I want to open a database. So a database is really just an associative array that's going to be stored on disk. So I can use this gdbm open. And it looks like a regular open statement. So we give it the name of a file. This is a file that will be created on the disk. This is a block size. This is saying we want to open it for reading, and we want to be able to write to it. And if it doesn't exist, we want to create it. And this is a permission mask, so it's read, write by me, and no access to anybody else. And that's just initializing the system, and it gives me back this thing called DB, which is set up to be a GDBM file. So it's like a regular uppercase file, right? So these are all things set up in that include file. And once you have this DB object, you can do the following. You can say gdbm store, and you give it 4 arguments. You give it DB, that's the pointer to the database. You give it a key, which in this case is a string. You give it the data you want associated with that key, which is another string. And then the flag which says replace, which means if this key is already in there, change its value. If it's not in there, go ahead and add it. And data is a structure in itself. So data is a datum. And a datum is a structure that has 2 fields. It has a data pointer and a size. So for example, if I want to store a piece of information, I set up the D pointer field to be the address of the string, but then I also set up the D size to be the number of characters in there. So this is a very general operation. We're simply taking a collection of bytes from memory and saying store this associated with that key. Okay. Now I'm using strings, so they're null terminated, but GDBM doesn't care about that. It's just taking bytes and storing them. So you can use it not just for strings, but for numbers, or characters, or linked lists, or memory addresses, or executable files, or whatever you want. It's totally general purpose. And so you can store things into the database. by using GDBM store. And you can read things from the database by saying, here's a key, go ahead and fetch that key. So call GDBM fetch, passes the database and the key, it'll pass back a datum, which is the data associated with it. And if the size of that datum is 0, it means it didn't find the key. Otherwise, the D pointer points you to the actual bytes, which in this case is a string. So we can go ahead and print it out. And there's also a way to iterate through all of the keys. So we can make a key, which is a datum from GDBM first key. So that gives us a key. But after that, every time that we say GDBM next key, and we pass that key that we got, it'll give us another key. This is the problem that we had with awk and bash. If you have an associative array, if you know the index of an element, it's easy to retrieve it. But if you don't know what the indexes are, how can you print out all the stuff that's in that array? We can't just say for I equals 0 to 4. We'd have to say print out data Izad, data Nick, data Scott, data Tina. And if there's a Carol, we have to know we have to say print data Carol. So you always need a way to go through all of the keys. So in bash, there was a for each, right, that we could use. In GDBM, we have this first key and next key pair. And next key basically just gives us successive keys until it comes back with a null pointer, and then we're done. We've seen all the keys. And then GDBM close just closes the database. So this is just sample code that I put together that basically lets me store and retrieve things from the database.
This next key, does that follow like a linked list or something? Is it keeping track of the address of each one?
It has a way to get through all the keys without repetition, without missing any of them. But how is it implemented? Don't know. You could do it with a linked list, but probably that's not what's being done, because they're implementing a hash for this, presumably, and we'll see how to do this with a hash in a little bit. So just for kicks, I'll compile this up and run it, and so we can store, retrieve, or dump data. So let's store some data, and I'll use my unimaginative sample. So we'll store Nick, and I'm going to teach art, and we'll store Scott. We'll let him teach computer science. We'll store Tina, and she can teach ME. And we'll leave it at that. So I can say retrieve, and let's see what Nick teaches, and I teach art. And I can say, let's see what Barney teaches, and it'll say key null not found. So Barney's not in there. And if I want to see everything that's in here, I can say dump, and it'll use that first key, next key, and it shows me all my pairs in my data. And I can quit out of there. And there's the database file that it created. And we can try to look at it, but it's mostly gibberish to us. But it's got information in there.
Why does it list what order that it is?
Why does it what?
Why is it listed in that order?
No way to know. So there's no guarantee on the order in which you're going to get these keys out when you say first key, next key. The only guarantee is that you will get every key exactly once and you won't miss any. But that's something to keep in mind, and we're going to talk about this a lot in 223. These are called iterators. And anytime you have a structure that you don't have, a predefined way of going through all the elements, you usually have an iterator of some sort that gives you the elements one at a time, usually with no guarantee on the order. So this ordering, no idea why it did that, but we'll see some possible reasons. And if I go back in here, since this is writing the database out on the disk, everything is still here, so I can say, let's see what Scott does. And there's Scott teaching CS.
Because all of them right now have completely different data.
Mm-hmm.
There's only one E, one CS.
Okay.
So if you put in like two more of like two of them.
Okay, so we'll have, we'll let Barney be a CS teacher. And we'll let Bob be a CS teacher. Right, so all that information is still in there. So I can retrieve Scott. Scott teaches CS, I can retrieve Barney. Teaches CS, I can retrieve Izad, he's still teaching EE. And it really doesn't care what the data is that's associated with each index. Now if I say store Izad, and we'll let Izad teach art with me, right? Then that should have overwritten Izad, and now he's teaching art. Bob never got written? Oh yeah, I just did that, all right.
Tigger taught CS last year.
Did he?
Yeah.
Oh.
I took it with it.
That's true.
Well, I think he was a guest lecturer.
Yeah.
Just, Tigger.
And the Stay Puft Marshmallow Man the year before.
He wanted to take the guest again,
All right, so
he left.
that's an example of how we can use this in C, and most languages have a way to give you access to an associative array or a hash. And like I say, it's generally a really useful modality for storing information. And this is one of those many things that personally, at least once I encountered it, everything became a hash problem, right? It became my hammer for about a month or two. I was writing a lot of compilers, and when you want to compile code, you need to collect a list of the variables, and you need to know where those variables are going to be stored in memory, right? Well, using an associative array, it's really easy to collect that information. First time you find a variable, look in your hash, see if it's already in there. If it's not, it's new, so figure out where to store it in memory, which is usually the next location that we haven't used yet. And then write an entry into the hash with the variable name and the location where it's stored. And now while you're compiling the rest of your code, when you encounter that variable, you just go into your hash with the variable name. It tells you where it's going to be stored in memory. And you can write your assembly language code like that. Or if you're interpreting, you can actually store the value of variables in there and update that based on what your statements are doing and such. So it's a pretty useful mechanism. So how do we make this work? So implementation. Well, we want some kind of box. We basically send in a key and we get out a piece of data. And this is our hash. So that's how we visualize this thing. You just put a key into this thing, turn the crank, and out pops the data associated with that. Or, you know, something saying there's no data in there to match it. And if you want to store something, you somehow put in a key in a piece of data and say store it. And if you want to delete something, you put in a key and you say delete it. But you use the hash. This is really what we're picturing. It's a box, put in a key, get out a piece of data. All right, so here's one way that we can do this. We can implement this with an array. So let's make an array of strings. So each entry in this array is going to be a car star. And we're going to have, let's say, 10 entries. All right. And we want to store Izad and CS. Well, we're going to find some way to associate with this string IZAD a number between 0 and 9. So what can we do? Well, we could take the ASCII code for I, add the ASCII code for Z, add the ASCII code for A, add the ASCII code for D, and then just reduce that modulo 10. And that'll give us a number between 0 and 9. I don't want to do the math, so let's suppose this equals 317. Reduce it modulo 10, we get a 7. So at entry 7, I'm going to store CS. And now, when we want to store Nick and Art, we add up the ASCII codes for my name. And let's suppose that this comes out to 265. And reduce it modulo 10, and that gives us a 5. So at index 5, we're going to store the data associated with me. Now, if I want to retrieve the information associated with Izad, what do? I take the ASCII code for I, Z, A, and D, add them up, reduce modulo 10, I get a 7. I go to entry 7 in our array, I get CS. I'm done. So this is called a hash function. And here's the idea. Hash function f is a hash function. F of some key gives you an index into this array. So if I want to find what Scott's position is, I could take Scott, put it into this hash function, which takes a string, gives me back an index. Maybe it gives me back the index 2. I look at entry 2 and it's blank. I know that Scott's not in this array, this hash. So the amount of time it takes to store something or to retrieve something is purely based on how long it takes this hash function to operate on a key. Take in a string of characters, return an integer from 0 to 9. However long that takes, that's how long my search and retrieval operations take.
So random question, but say you were doing like a list of all the students in Clark.
Mm-hmm.
What would you do if 2 students happen to be named like, I don't know, John Smith or something?
Well, that would be a problem. So if we had 2 teachers named Izad, right, this is definitely not going to work. You got to have something, so you call them Izad 1 and Izad 2 or something like that, or John Smith 1 or John Smith 2. Or you do what we do at Clark, and we use a student ID, which is unique. So we would key this off of student ID instead of name.
Did you use modulo 10 because there's 10?
Mm-hmm.
Okay.
Yeah, I wanted a number to come out between 0 and 9.
So I'm assuming, like, I guess already you addressed the problem either by using uppercase, all lowercase, or student ID, but if you had something like where you were using an all uppercase or an all lowercase system, and you had something named Bill and something named Lib, you would return the same value.
Yes. All right, so here's the first. Yeah.
So that was 10. You're going to have 10 things.
Mm-hmm.
You don't know how many you're going to have. What do you do modulo?
You do modulo however big the table size is,
So you need
and you make a decision in the beginning. But we're going to get into that too, because it's going to come off Bill and Lib. So yeah, Bill and Lib, our new teacher, right? If our function is simply to add up the ASCII codes and reduce modulo 10, this and this are going to give me the same value. And that's kind of a problem, because if I enter Bill first and Bill hashes to index 1, I'm going to put their field right here, and then I get Lib and I hash Lib, and they're going to hash to index 1. Either I overwrite Bill's information, or I have to say, hey, I can't store this other person because that space is occupied. Neither of those are acceptable.
Doesn't capitalizing your first letter actually change that?
It changes that, and you can do other things. For example, I could do the first letter's ASCII plus twice the second letter's ASCII plus 3 times the third letter plus 4 times the fourth letter. And now the position in the name is going to make a difference. But there's a fundamental problem that we're skirting around, which is if I only have 10 entries in my hash, and I have potentially, 10,000 different names, thousands of names are all going to map to the same one of those 10 indexes, right? Because 10,000 names, if they all map to something between 0 and 9, right? It's not an injective function. I have these many things all mapping to 0, and all of these things map to 1, and all of these map to 2. And that's unavoidable unless your hash table is big enough to contain every single entry uniquely. And that's really not feasible.
Would that be sort of a good thing, though, in the case of, like, I wanted to search CS and get a bunch of names that all tie to CS?
You could do that. I mean, that could be an advantage. But there'd probably be different ways to do that. But yeah, that might be one way to make lemonade. So let's look at a different example. Let's hash Clark student IDs. So I'm going to make an array of 1,000 entries. And what I'm going to do is I'm going to take the first 3 numbers of the student ID and use that as an index in this array. So your student ID is 940451234. I'm going to look at the first 3 digits, 940, and I'm going to put you right here at index 940. And as soon as I get a second student, well, their number is probably going to start with 940 also. And it's going to try to store it in exactly the same spot. That's a really, really poor choice of a hash function. Okay? And I know that's a poor choice because I understand something about the nature of the data I'm trying to store in this hash. I'm storing student IDs and names. Most of the student IDs start with a 940. And most of the middle digits come from one of 3 or 4 possible values, 40, 45, things like that. So that's a poor choice of a hash function. Here's a better choice of a hash function. Let's take the last 4 digits. And let's make an array of 10,000 entries. And let's just take those 4 digits and use that as an index into our hash. That's going to be pretty unlikely to have a collision. There may be 2 students. There may be a 940441234 that would collide. Now, how could I guarantee that I never have a collision with student IDs? Use the full ID. So if I make this thing, it's either 10 or 100 million entries, and I say take the entire ID and use that as an index into my array, I'm not going to have a collision because no 2 students have the same student ID. But that's a huge array, and most of that array is not going to be used. Because if there's a, so let's see how big this is. That's going to be 100,000, 10,000, 100,000 million, 10 million, 100 million. It's going to be 1 billion entries. And we're not going to have 1 billion students at Clark. Not this year. Right, so that's avoiding this conflict of indexes, but it's very inefficient. So hashing is kind of trying to find a sweet spot. So I might actually stick to just 1,000 entries, and I might just take the last 3 digits and say that's what I'm going to use to find where this entry is stored. Now I've only got 1,000 entries. I know I've got 10,000-ish students at Clark, so I'm not wasting space, but I'm still going to have collisions, but not too many collisions. But we do have to deal with collisions. So a collision, so when 2 keys map to the same index, that's called a collision. Or a hash clash sometimes. And there's different ways to deal with this. So let me show a very straightforward way to deal with it. So we take our first student ID, 234 is the key. And this is Jane. So we'd like to store Jane's name at that location. And now another student comes in. And this is a purple dinosaur. 4234, and we'd like to store 4234 hashes to location 234. We'd like to store Barney there, but Jane is already in that location. Well, instead of actually storing a name in this array, here's what we can do. We can make this an array of pointers, and we can build a linked list. And now when we find Barney, Barney comes to location 234. We can say, okay, go ahead and add to that linked list a node named Barney. And we can extend it using everything we know about linked lists. And now I'm never going to run out of space unless I run out of memory on the system. I can have 5,000 names that all hash to location 234. I'm just going to get a really long linked list. But my order 1 behavior is no longer valid. Because if I have 100 names in a linked list here, and I'm looking for a name that hashes to 234, I've got to do 100 operations potentially to find that name in the list. And as the size of this list grows, my performance degrades. So I'm back to something like an order n, but not quite as bad as just, an array of n entries. And now my keys aren't unique, so I also need to store another piece of information in here, which would be the full student ID. Thank you. So that's a pretty straightforward way to deal with collisions. And it takes some overhead, and it'll degrade your performance somewhat. But you don't run out of space this way, right, until you run out of memory. So this is something called chaining. All right, let me show you a different way to deal with collisions. And this is an approach called probing. So we take our hash function. It takes a key in and it gives us back an index into our array. But we now make our hash function accept a second argument, which we call the probe. And this gives us an index. And depending on the value of the probe, 0, 1, 2, 3, 4, this key will map to a different index. So let's look at a simple example. Let's just store, integers. So I'm going to stick to a basic hash function that just works modulo 10. And here's what we're going to do. F of key, comma probe, equals key plus probe, modulo 10. Okay, to store 12, we calculate f of 12 comma 0. And that gives us a 2, and location 2 is free. So we're going to store our number 12 right here. To store 33, we're going to do f of 33 comma 0, and that's going to be equal to 3, and location 3 is free, so we'll store a 33 right there. Okay, to store 43, we'll calculate f of 43 comma 0. 43 mod 10 is 3, so that's going to give us a 3. We look at location 3, we have a collision. Okay, this is a collision. So now we're going to find f of 43 comma 1. We increase the probe. 43 comma 1 says 43 plus 1 is 44, modulo 10, that's a 4. Location 4 is free. This is where we store our 43. All right, one more. Let's store 102. So f of 102 comma 0 is going to be 2. That's a collision. So increase the probe f of 102 comma 1. That's 103 mod 10 is a 3. That's also a collision. So increase the probe f of 102 comma 2. That's a 4. That's also a collision. Increase the probe again. F of 102 comma 3. That's 105 mod 10 is 5. No collision. This is where we store 102. So the probe is basically poking around in your hash looking for an open spot, right? Probe is 0. You get a location. You stick in there and see if it's free. And if it's not, you calculate another spot by using a probe of 1 and you check there. And this is not a very good probing function because we're getting what's called clustering. Our entries are bundling up in one area of our array and the rest of the area is pretty much unused. So a better function might be, for example, to take the key plus the square of the probe. So now if this spot's in use, we're going to jump down 4 locations and then we'll jump down 9 locations and so on. And it'll tend to spread things out more. But this idea of using 2 inputs to your hash function, the thing you want to hash and then an attempt number, a probe number, that's what probing is.
Then do you have to keep track of the probe when you want to retrieve your data?
Yes, so if you want to look for the number 102, you can't just hash 102 to a 2 and look here and say, nope, 102 is not there, that's a 12. You've got to realize that because there's a 12 in here, you might have had a collision when you stored 102. So you'll rehash with a 1, check 3, and so on. Right? So the number of probes that you have to make directly degrades your performance. This gets even worse when you delete. We'll talk about deletion on Wednesday. But basically, if I delete the 12, and now I look for a 102, I apply probe 0, f of 102, 0 is 2. I look, that spot looks empty. Can I conclude 102 is not in my table? No, it actually is. It used to have a collision there, but since I deleted something, it looks like there's no collision. So I need to remember that there was something there. So that starts getting a little more complicated. But it's not too bad when you do it calmly. So I'm not giving you a hash assignment this quarter, but I'll probably give you some ODPs to work with some of these concepts. Yeah? Sure. Yeah, that would make it more efficient. Your ideal hope is that you just don't have too many collisions, though. So based on the nature of the data, you decide on a hash function and a size for the array, and hopefully you're minimizing. If you're getting thousands of things chaining off of there, it's probably not the best design for a hash. You probably want a bigger table, or if you're getting clustering, you want a different hash function. I don't know what they use. I don't think so. But, well, I mean, databases use this kind of thing internally. But I don't know what gets used by what.
So that would kind of make sense why when people's names are listed, they go off of the last name first, because that's more unique.
Yeah, definitely.
Oh, yeah.
Yeah. And there's usually varieties of first names, right? So Bill and William, whereas last name tends to be rigidly specified. All right, so we'll talk more about this on Wednesday, and we'll go over your midterm.